In natural systems, I mean, the normal kind of river that you would see as you walk around the Earth, flow is turbulent. Water has a low viscosity. Water has a high density. Rivers are usually sort of order, a few tens of centimeters to a few meters deep. And flows are usually moving at about 1 meter per second. And so if you go back and look at the Reynolds number, those flows are definitely in the turbulent realm. And so we might want to know what that means for how the flow behaves and what these eddies that are associated with turbulence might be doing to the properties of that flow and what we measure, and how that might affect the velocity profile, how sediment is transported, and how rivers overall shape their beds and banks. So this figure right here, which I'm borrowing from Heidi Neff's course notes because I think it's fantastic, is showing this transition between laminar and turbulent flow. And a couple lectures ago, we sketched that out ourselves. But let's just look at it here again. So what I'm pretending right now is that we have some sort of injection tool, so some sort of like eyedropper right here. And so what I'm going to draw is just this little dropper that we're using to insert the tiniest bead of dye into the flow right there. And that red dye trace, and I should actually draw it directly straight on here and just draw like a dot. So that's where it's starting. So that dye trace is continuing to be one smooth flat line inside the laminar portion, and that's because there isn't any turbulent mixing up and down. If something's entered into the flow, it will stay at that level in the flow. But at some point, the inertial forces that are driving the formation of these eddies overcomes the ability of viscous forces to dampen them out, and the flow will start to be whipped around by these eddies up and down and start to diffuse this whole dye trace into the larger body of the flow. So if we look at a couple points here, we're going to make 2 points. The first point is going to be at the head of this arrow, and I'm going to call this point B. Heidi's already labeled A over there. So the point B at the head of the arrow is going to experience a single constant velocity. But on the other hand, this point A, which is right over there, is going to have velocity that looks something more like this. And so over here we have the downstream velocity, which is u bar. And down here we have the cross-stream velocity, which is v bar. So the u and the v here that we're drawing, so this is u, this is v, are instantaneous velocities, whereas this v bar, which equals 0, and u bar, which equals something, which definitely is greater than 0, are the mean values of those. And you can see that there are a bunch of fluctuations around this mean. So why is that the case? Why are the velocities fluctuating up and down so much? Well, first let's think about how we can just describe this in a sort of simple mathematical way. And before we even do that, let's think about this physically. So if we have a river channel, and we're going to have flow in this channel moving towards us, so flow moving towards us, one thing that we know is that there isn't going to be able to be any net cross-stream velocity, and that's because the channel walls are in the way, right? So if all the flow starts moving over this way, it's just going to pile up and then flow back over to that side. So there are no net cross-stream velocities. Velocity in this direction is 0, so no net cross-stream velocity. But downstream, we know the flow is moving towards us, so there is a net downstream velocity. And both of these have these fluctuations associated with them. And so when we describe them, we say that u is going to be equal to u bar, which is this mean, plus u prime, which is the size of these different fluctuations. So what are these? Why are they important? So these velocity fluctuations are describing how flow at a single point in the channel might vary through time. And they're important because they're actually mixing the flow and imparting momentum to particles inside of it. And so let's just do a quick thought experiment and imagine how these velocity fluctuations might relate back to turbulence. So if we're at a point in the stream, I'm going to draw this point in black 4 times. And then I'm going to draw this eddy going through it in 4 different positions. So if we have this whirl, it could be going like this, or it could be passing through the point like this, or perhaps it's passing through on this part of its path, or maybe it's actually over on, oh, I knew I was going to mess up one of these. Let's do this side of the whirl. Now let's think about what the velocity looks like. Let's plot it together. So if I just draw, I'm going to switch back to black here, a plot of u versus time, assuming that we have these 4 different eddy positions that are going on like that, and then we have u bar. Gotta try to make that a little bit straighter. U bar right there, so that's our average velocity. Let's draw our real u like this. So here, this eddy is carrying the flow up. So there's going to be no difference, and so velocity is just going to equal u bar. Here though, the eddy's pulling that flow forward, so we're going to have some excess velocity. Here, it's pulling the flow back down, and so since down is not forward or backward, the velocity is going to stay the same. And here, this eddy is pushing the flow backwards, so we're going to get a value where the eddy is actually subtracting a little bit off from that mean velocity. And so from this, we end up getting something that looks like this, where we have this mean velocity and then we have the variation about it. And so these variations in velocity then are, let me write this out, variations in velocity relate to turbulent eddies pushing parcels of flow. So we have a term that we use to describe the intensity of turbulence, and that's something that we call the shear velocity, or sometimes friction velocity. So if we want to know how big these eddies are, we want to talk a little bit about how strong the shear velocity term is, and the shear velocity in fact relates to the shear stress in the channel. And so that's going to be our next topic, is going inside, kind of unpacking what causes different stresses to exist within a flow, and then thinking about how those stresses can set up toroidal motions, or can set up spinning motions, and how those spinning motions then become the eddies that we see in natural turbulent flows.